The most recent examination results propose that something emotional once occurred in the nearby planetary group a long period of time back. An unfamiliar star slammed into our home world and drew nearer to our focal star than the Voyager probes are today. Indeed, the results of the stellar visitor might still be felt. It not only drastically changed the orbits of the trans-Neptunian objects, but also significantly impacted the moons of the large gas planets. But how did this stellar encounter unfold in detail? Why did it have such a significant effect on the structure of the nearby planetary system? And what lessons might experts gain from this unique experience? Further and further into interstellar space venture the two NASA probes, Voyager 1 and 2. When it comes to the subject of the most distant stations of humanity, there is no surpassing these world-renowned sister probes. No surprise, although the identical spacecraft only set out into space in 1977 to gather new data about the outer planets of the planetary system, they have now journeyed into interstellar space. Communicated in numbers, this means that Voyager 1 and 2 have now put an incredible distance of 24.6 and 20.6 billion kilometers, respectively, between themselves and the Sun. And while the Voyager probes are giving us unprecedented insights into unknown cosmic realms, we shouldn't forget that it also works the other way around. In fact, a new research study suggests the surprising conclusion that a foreign star once entered the solar system, and in doing so, remarkably reduced the distance that currently exists between our host star and the Voyager probes. But what's behind it? And how could this stellar encounter help us solve some tantalizing mysteries of our home system? Well, to understand this, we need to venture a little way into the universe of the moons of the nearby planetary group, and bear in mind that these occasionally display completely disconnected characteristics. On one hand, there are the satellites that behave as one would expect. These include Earth's moon, which orbits our blue home planet in a prograde fashion, in other words, following the direction of Earth's rotation. However, the main point is that this arrangement doesn't apply to all satellites in the solar system. The outer planets, like Jupiter and Saturn, have a remarkably large number of companions that, to put it simply, move the wrong way around. Or, in more technical terms, they orbit retrograde around their planetary centers. In general, the retrograde moons orbit against the rotation of their planets, and often also in highly inclined, elliptical orbits. The contrasting moon patterns are by no means uniformly aligned. Quite the opposite. In the case of Jupiter, experts count 71 retrograde satellites, while the mighty gas giant simultaneously has only 16 prograde satellites. In the Saturn system, the differences are even more pronounced. Here, the ratio of retrograde to prograde moons is 100 to 22. Where do the retrograde moons come from? What is the reason for this unusual constellation? Well, in short, experts have long assumed that the retrograde moons are, to put it casually, newcomers. Unlike their prograde counterparts, these satellites didn't form together with their planets, but rather formed in a completely different part of the solar system. Specifically, researchers traced the origins of these satellites to the remote Kuiper Belt, a ring-shaped region beyond Neptune's orbit. Scientists believe that most medium-period comets originate here, and that objects from this area somehow became retrograde moons by falling under the gravitational influence of the large gas planets. But what caused this? For a long time, astronomers pointed to the Jovian migration. According to this hypothesis, Jupiter initially formed farther out and then gradually migrated inward. This movement was only halted by the formation of Saturn, which ultimately positioned the king of the solar system in its current orbit. However, this early journey didn't resemble a gentle stroll, but rather a proverbial bull in a china shop. As Jupiter moved through the early solar system, like an oversized wrecking ball, it triggered a massive collision cascade of countless planetesimals, or planet seeds. Thus, the inner solar system was practically cleared out, paving the way for the formation of smaller, rocky planets low in gas. Without Jupiter's movement, there might not have been either Earth or the other terrestrial planets in the solar system. The retrograde moons are also thought to be remnants of this rough journey. However, this assumption has a small but critical flaw. It cannot explain all the properties of the moons in question. Thus, a team led by Suzanne Veris from the Jülich Research Center, along with colleagues from the Dutch University of Leiden, sought an alternative explanation. They focused on the close flyby of a foreign star, a brilliant encounter with consequences. As previously mentioned, our solar system doesn't end with Neptune. In fact, researchers are now aware of several thousand celestial bodies moving through the trans-Neptunian region. It's even believed that there are several million bodies with diameters exceeding 100 kilometers. However, surprisingly, many trans-Neptunian objects follow unpredictable orbits that deviate from the typical orbital plane of the planets in the solar system. To uncover the reasons behind these unique orbital characteristics, Vera and her colleagues, Anthony Gonzalez and Simon Porteges from the University of Leiden, conducted more than 3,000 virtual encounters. In the end, they concluded that the unusual orbits of the trans-Neptunian objects could indeed be attributed to the influence of a foreign star. The three astrophysicists found that this could explain the orbits of very distant objects, like the dwarf planet Sedna, discovered in 2003. Sedna orbits the Sun in an extremely elongated orbit that takes it as far as 17 astronomical units from our Sun. As a regular observer, you may know that an astronomical unit, AU, represents the average distance between the Sun and Earth, which is about 150 million kilometers. But if you follow Veris and her colleagues' explanations, the aftereffects of the stellar close encounter could also account for the characteristics of objects that orbit almost perpendicular to the planetary orbits. This also applies to 2008 KV-42 and 2011 KT-19, which orbit in the opposite direction to the planets. Specifically, this explanation posits a star that was slightly less massive than the Sun, about 0.8 solar masses. According to the model, it passed at an angle of about 70 degrees to the planetary plane and approached significantly closer to the Sun than the current distance of the Voyager probes. While the Voyager probes are now 24.6 and 20.6 billion kilometers from our parent star, the close stellar encounter might have come as close as 16.5 billion kilometers, 110 astronomical units, about 4 times the distance between Neptune and the Sun. Even the aforementioned ratio of prograde to retrograde moons could be replicated in the simulation. In the Jupiter region, the probability that trans-Neptunian objects would end up in a retrograde orbit was 3 times higher than in a prograde one. The situation was quite similar in the Saturn system. Although most of these newcomers were later ejected from their new orbits, enough remained to establish the current group of irregular moons. The irregular moons are characterized not only by their mostly retrograde orbits but also by the larger inclinations, eccentricities, and distances of their orbits. And if scientists are to be believed, the true beauty of their model lies in its simplicity. After all, a single cause can answer so many open questions about our solar system. Furthermore, it's even possible that our solar system would never have existed as we know it without the close flyby of another neighboring star. Another intriguing hypothesis is based on the approach that, around 4 billion years ago, a star the size of the Sun passed through the young solar system, tearing a significant part of the primordial cloud with it. According to Vera, the protoplanetary disk was essentially damaged in the process, reducing the mass of the Kuiper Belt region to about 1% of its original mass. What was nearly a catastrophe in the distant past now serves as a possible explanation for the orbits of many trans-Neptunian objects and the sparse population of the Kuiper Belt.